The makeup of the Earth seems like a simple topic at first. We know that the denser elements lie at the centre, like iron, while the lighter elements make up the crust. But have you ever wondered why the composition of the Earth is so different from the composition of the universe? Shouldn't they both be the same? This table that I've made ranks the most abundant elements in the Earth's crust and the most abundant elements in the universe from 1 to 10. As you can see from this, there is almost nothing shared in common, and even in cases where the same element appears, they're in different spots, as you can tell by the lines I've added. For example, oxygen is the most abundant element in the Earth's crust, but it's only the third most abundant element in the universe. Hydrogen is an even more poignant example of this. It's the most abundant element in the universe, but it's only the 10th most abundant in the Earth's crust, having only a single figure percentage abundance. Now, let's take a look at why this might be. To do this, we'll have to look at the birth of stars. When a star is born, it begins to emit a solar wind, which consists of electrons, protons, and alpha particles. You've probably heard of this term before. Let me explain a bit more. Okay, for this demonstration, I have two seemingly random objects. I have a roll of duct tape and a scrunched up ball of paper. Now, I'm going to use my breath to demonstrate the effect of solar winds on atoms. So, for this, I'm going to have to ask you to imagine that this is an iron molecule, or atom, sorry, and this is an atom of hydrogen. Now, I'm going to place this here and blow on it, simulating solar wind hitting an atom. There's very little movement, and there's no surprises there. This is pretty heavy. Now, let me blow on this hydrogen atom. It's gone. Now let me explain that further. That experiment, which may have seemed simple at first, is actually one of the main reasons why the planets in our solar system are how they are. The gas giants are actually the first planets to have formed. This is because they formed their core and then trapped the gas before it was pushed away out of our solar system by the sun's solar winds. Earth and Mercury, on the other hand, haven't had the chance to do this as they'd formed less recently, and their cores didn't form in time before the gas got swept away. This is essentially why Earth doesn't have the same composition as the rest of the universe. The composition may be similar in a planet like Jupiter or Saturn. Even though it might not be identical, it may be similar. Let me get into that a bit more. There are actually currently 3 major models for the formation of planets in the solar system. They're all different, and they have different names, but they kind of describe the same events. These 3 models are the disk instability model, the pebble accretion model, and the core accretion model. These may sound daunting at first, but I'll do my best to explain them as they're a bit more simple than they may seem. Okay, so before I start this rather strange demonstration, let me explain something about how the solar system forms. Now, when the sun has just formed, all the gases and elements form a disk around it. Now this is pretty much because the rest of the galaxy forms a disk as well, so the actual gravitational pull of the entire galaxy will pull the plane of the solar system into line, which is why we have that kind of flat look to the solar system. Now, what I'm doing with this demonstration is I'm going to try and explain the core accretion model. Now, pretty much what this means is you'll get some of these particles and they'll start to lump together, right? Different elements. And then that will have a more higher gravitational pull, so it starts pulling more in and more in. And this kind of works like a snowball effect, and eventually it'll start forming a small core, and then that will start attracting more and more until you form a planet. It's pretty simple. Okay, so the second model is the disk instability model. Now, the problem with core accretion is it doesn't explain how gas giants formed fast enough to actually trap gas, and the disk instability model kind of gives this a shot. Now, I talked about this plane that forms around the new sun, and basically this model assumes that this disk is not entirely symmetrical in every way, so there's going to be areas of higher concentration of gas and lower concentration of gas. And pretty much this model just describes how these higher concentrations of gas kind of collapse into themselves and start making their own gravitational pull. And then this just pulls in more and more gas, and this is effectively what ends up forming the gas giant, with a bit of heavy elements getting pulled in as well to make the core. I decided that this model might be a bit hard to model with paper shreddings, so I decided to use this diagram of a computer simulation, and this pretty much just shows 4 images over a certain amount of time showing how these lumps of gas kind of collapse into themselves and start forming planets. The final process for the formation of planets is the pebble accretion model. During the time when there's planets forming, there are lots of these small pebbles ranging up to about 1 meter drifting around the solar plane. The larger formed planets, say like Jupiter's core, would attract these more frequently and basically steal them from the smaller masses like Earth. This would allow them to grow faster. You can imagine this like the rich stealing from the poor, because this is pretty much what happens. There's not much left over for the smaller planets, but the larger planets can grow at an increased rate. And this actually explains and allows for the larger gas giants to have formed in the outer solar system, because this model allows them to grow fast enough to trap this gas before it's swept away by the solar wind. In reality, though it may seem a daunting topic, the matter of the formation of planets is actually rather simple. It pretty much boils down to the newly forming planets forming either fast or slow. The fast ones can trap gas, and the slow ones can't, or can't do so as much. This is fundamentally why Earth doesn't have as much gas in the atmosphere as Jupiter, because all these other elements have been blown away. And if you think of it like that, that's also the reason why the Earth's composition isn't the same as the universe, because a lot of these lighter particles have been blown away before Earth has had a chance to actually catch them. So it makes sense then that Earth is more made up of heavier elements. I hope you enjoyed listening, I hope it made sense to you, and thank you.